And we are talking about something called an enol and then an enolate. And the idea now is that we have compounds that can be deprotonated, particularly at the alpha position. We talked about the definitions of these things. We talked about how to go between the enol and the keto form by different types of catalysis, maybe base, maybe acid. And we talked about the potential uses of this thing in terms of the use of these alpha carbons to be able to do organic chemistry. We talked about bases, and we talked about what type of bases you would have to use. A weaker base will give you an equilibrium with an aldehyde or a ketone, and a strong, powerful base such as LDA will take the equilibrium to the right-hand side, and all that's left is the enolate form. And we'll do more of that in the near future. But what I want to get through today is this idea of this alpha bromination reaction, because this sets up the proof, I think, for why enols are important. If you look at the starting material here, we have cyclohexanone. It doesn't have any nucleophilic component at the alpha carbon. We've seen Br behave as a radical. We've seen Br behave as an anion, and sometimes as delta positive. In this case, it's going to behave as delta positive. And again, I can't see anything here that allows us to try and explain that. So what we need to worry about now is the fact that we will have to form an enol. The enol becomes part of the mechanism, and the enol is then the nucleophilic component that goes after the bromine. We'll see again today that if you start out with an unsymmetrical ketone like this one, where you have alpha protons at this position and at this position, you can get two different products. And the outcome here will be based on how much of each enol you have, and that will be based on the Zaitsev idea of stability. So in that case, you get two different materials. It turns out that the more highly substituted one is major and the lesser substituted one is minor, and not because necessarily the stability of the products, but because of the amount of the intermediates that you have, amount of enols that you have. So we did look at the mechanism. We'll start here again and think about the consequences now of having gone into 22 and having activated CH bonds. 22 is all about activating CH bonds with electron withdrawing groups. In order to get from this ketone starter material down to this alpha bromo material, it's not as simple as it looks. It certainly involves a bunch of steps in which we protonate to make something more reactive, as we usually do. If there's a proton, protonate something. And we'll end up then with an E1 type process to give us the enol. So acid catalysis does speed up the formation of the enol, and then the enol can be used subsequently in the chemical reaction to give you the bromide. So what is this behaving as? Give me an idea of what that's behaving as. It's a nucleophile. Absolutely, it's a nucleophile. And it's more nucleophilic than a regular double bond. The double bond can push electrons towards something positive, but here we have the hydroxyl group that can push electrons in. That can help speed things up. It can also help stabilize the intermediates. And I think we developed on Friday last week that this is simply a Markovnikov addition in which you go through the beta-carbocation. And we want to put the positive charge next to the oxygen here because it will be stabilized by resonance. Again, the textbook sometimes skips the resonance structures. I'd like to see one here to explain why this is so good. And then finally, you lose a proton, you get to the product. So in sort of, you know, from my perspective, this reaction tells you there must be enols in there. You can see them spectroscopically, you can see them in infrared, you can see them in in proton spectra. This gives you some chemical proof as to their presence. They have to be present to have a nucleophile in there. So what we left off with was this idea again of talking about selectivity, talking about regioselectivity in terms of where things go. And I think everybody should be happy now with this idea that the more substituted double bond is going to be favored, right? In the enol form. So you could take off a proton on the left or on the right. On the right, you get this enol at the bottom. On the left, you get that enol down there. And the one on the left is more stabilized because of the fact that it has more alkyl groups attached, and that's simply the idea of Zaitsev rule, right? So that one is going to be more in there, and that's going to lead to this product as the major product. After that, mechanism is the same. Get to the enol through acid catalysis, and then brominate. The alpha bromination reaction does have some use. You can then replace the bromine with nucleophiles, or you can replace it with metal, for example, and do other chemistry after that. But we just use this to get into the alpha chemistry, the alpha carbon chemistry, to highlight the fact that it has to be activated, and in fact, those protons at the alpha position are activated. We're going to use these materials to make this type of product. And this is something called an alpha-beta unsaturated ketone. But those things are very, very potent electrophiles, and we'll use them in all sorts of different chemistry to be able to activate and be able to derivatize them to be able to make more interesting materials. So the alpha carbon, again, is just the one next to the carbonyl. The beta carbon, obviously, is the one next to it. And we can say now that what's happening here is an old reaction in which a base comes in, grabs a proton, and eliminates. Any idea what type of mechanism this will be? What sort of molecularity will it be? E2, right? So basic conditions going after the proton, taking it off. We have to have somewhere to put those electrons. In this case, it's going to be to the bromine. You're swapping maybe O- for Br-, which is always a good thing. And in this case, you end up with a pi bond, and that is an alpha-beta unsaturated ketone. So down here, we have a synthetic sequence that we can employ to be able to do this. We can start out with a ketone. We can then take off this proton in the formation of the enol, or this one, and we get this is the major product again. The right-hand side is favored here because the double bond came about through halogenation at that position, which came about through the more stable enol. Just add those ideas together, you get that outcome. And again here, we're using those conditions. Classically, if you look for those, you'll do an alpha bromination. What temperature would you run this at? If you had to set this up in the lab, what would you run it at? High or low? Low, why? To avoid radicals. If you formed radicals, they would do all sorts of things that you don't want. And so here we're doing electrophilic, nucleophilic chemistry, run it at low temperature, and away we go. So we get the bromination at the alpha position. Again, look at the regioselective outcome, the fact that this right-hand side is favored, and then do the E2 reaction. Pyridine's not that strong a base, but it's strong enough. And we'll talk about these compounds being desirable later. What is the relationship between those two double bonds? They are conjugated. Absolutely, they are conjugated. And so you don't need a very powerful base here because that conjugation is going to really help you out. Okay? Moving along, because I want to get to this one, the Hell reaction. All right, Professors Hell, Volhard, and Zelinsky came up with this one. It is nothing more complicated than what we just did, except it's applying the chemistry to a carboxylic acid. Now, this can be very useful because if you have this halogen at the alpha position and you replace it with an amine, some nitrogen compound, you make an amino acid. And everybody's at least heard of amino acids, and we'll talk about them in the next couple of weeks. Building blocks for proteins, incredibly important materials. So we can build them in the lab by, first of all, alpha halogenating a carboxylic acid, and then, after that, we do some substitution chemistry and make an alpha amino acid. Well, how do we do this? This is quite a complicated process. It's the same as what we just did, but a little bit of a complication. There's the alpha proton. Now, that proton is certainly not the most acidic proton on that molecule. So if you brought a base in, it'll certainly go after the carboxylic acid proton and take that off because the pK is about 5. If you put the proton here and you have alpha protons, we can get alpha halogenation. And again, the point is, as it stands, that carbon does not seem to have any nucleophilic properties whatsoever. So again, we can infer that maybe an enol gets formed in order to do the halogenation. And you'll see that there are definite parallels right here. The problem is, the amount of enol for a carboxylic acid is very, very low. Now, for a ketone, it was fairly low. For an aldehyde, maybe it's a little bit different. Whoops. But for carboxylic acid, it's pretty low. And the idea is that the carboxylic acid itself is quite stable. When you think about an equilibrium between an enol and the carboxylic acid, and the carboxylic acid is stabilized primarily by resonance from this lone pair here, then the carboxylic acid is preferred. And so in a solution, you're going to get pretty much all carboxylic acid and a very, very, very small amount of the enol. Not enough to make this react fast enough and go sort of fast enough as we want to. So what we do instead here is we modify the procedure. First of all, we take PBr3 and we treat that carboxylic acid, and very much like the mechanism for SOCl2, I'll show you in a second, we're going to form a bromide. And this is an acyl bromide. Now, it turns out the amount of enol in a solution of acyl bromide is more significant. There is more of the enol present if you put a bromine there than there is if you don't. Now, you might be able to work this one out. Why do you think this now has a chance? What do you know about bromine in terms of its lone pairs and in terms of spreading out and delocalizing? What do you think about bromine versus oxygen? What's the major difference? A little bit of electronegativity, but mostly what? Size, right? So the argument goes like this. In this molecule with the bromide right there, the bromide isn't as good at pushing electron density into the carbonyl. The bromide isn't as good at this as oxygen, right? Oxygen's very good at this over here because it's the same size as the carbonyl carbon next to it, and so that delocalization is pretty good. But if you go to the bromide, you get less delocalization. What does less delocalization mean? It means it destabilizes that molecule. It destabilizes the carbonyl versus the enol. It's not that the enol is that great, it's just that the carbonyl isn't as stable. So now we have an equilibrium that's kind of helpful. We now have a higher concentration of the enol, and so we get a reaction that's going to be better for us in terms of time. So let's get rid of all that noise. I'm going to show you a mechanism from my website in a second that sort of summarizes all this stuff. But so far we have a carboxylic acid being treated with a brominating agent that we have seen before. We have seen alcohols with PBr3 give bromides. This is just an extension of that. And we end up with an acid halide. And the acid halide has a significant amount of enol in solution, a tautomer. So after that, we have our lone pair here, our double bond. We can go after the bromine, kick out Br-, and we get an alpha bromo acyl bromide. That's not what we want. We're not quite there. What do you think we have? Well, it says there. What we need to add to get rid of that bromine is water, and everybody who's been practicing this stuff should be able to handle that. You've got a nucleophilic water, goes after the carbonyl, form a tetrahedral intermediate, lose the Br, and you have your carboxylic acid back. So I would argue that that's no more complicated than where we've been, just adding a few little things together. Now, from the website, you've got access to this. Don't forget all those mechanisms are there for you to practice. They work on your phone, your washing machine, whatever you use the internet on. Practice them. The more you see, the better you'll do. The better you do, the happier you'll be. How it works. Here we have this sort of rough mechanism for how this is going to happen. We have the possibility of PBr3 acting as a brominating agent. First of all, what we do is attack the phosphorus with an oxygen. And we've always said that oxygen-phosphorus bonds are desirable. They're quite strong. The Wittig reaction being the best example of that. So an oxygen-phosphorus bond gets formed, Br- comes back off, and we end up with this. So we've activated this as a leaving group. This guy here now is going to be a good leaving group. And if we do that 3 times on PBr3, because we have 3 bromides, we can replace 3 of them, we get this. All that will happen now is that the Br- will go after the carbonyl. We'll kick electrons up to the O. We'll form a tetrahedral intermediate. We'll collapse, lose the Br-, lose this leaving group over on the left, and we have a bromide. If you've been practicing acyl substitutions this weekend, that should be second nature by now. So what we've got here now is the acyl bromide. This is very much like the compounds we made earlier using SOCl2, and it's very similar to the ones we used for the Friedel-Crafts chemistry a while back. We have a potential leaving group. Now, we don't use it here as a leaving group, but what we're going to do now is rely on the fact that this is significant. There is a significant amount of the enol in there, and then we're going to do exactly what we did for the ketones in the previous section, in which we used the enol as a nucleophile. Go after bromine molecule now, right? So we're adding Br2. We're done with PBr3. We're now adding Br2. So you're going to get 2 brominations. In this case, we're going to add in a Markovnikov sense, because this carbocation is much better than the other possibility. If you added the bromine next to the oxygen, and you put the carbocation at the secondary position, that's not great. If you put the carbocation right there, you've got the possibility of resonance. And so now we have that right there, and all we need to do is lose a proton, and that gives us the product of step 2, the alpha-bromo-acyl bromide. After that, hydrolyze, there is a mechanism obviously. Water comes in, attacks the carbonyl, kicks out the bromide, and we end up here. So very useful stuff. And again, it sort of summarizes or sort of highlights the fact that you do need to have these enols in there to be able to do this chemistry. Otherwise, it just won't work. There's no other possibility. It's not radical chemistry, so there's no other way of substituting these molecules. And this is the bromoform reaction. The bromoform reaction is an interesting reaction that is changing the pH again. Often the pH makes a difference in terms of what happens. You might get similar outcomes, but we go through different pathways. And if I'm changing the pH to hydroxide, what are we dealing with here? Positive things or negative things? Negative every time. So once we've swapped proton for hydroxide, instead of protonating something, we ought to maybe be deprotonating something or attacking something. So again, what needs to happen here in this reaction is an alpha bromination in which hydroxide and bromine somehow get together and organize an alpha bromination. So we need to be looking at the change. And again, mechanistically, you've got to be aware of what the products are. So the first thing you do when you try to organize these equations is to write it down. What's the product? You know, where's the starting material? Here's the reagent. Here's the product. And if you don't do that, you have no chance of mechanism. And if you do that, you've got some chance now of recognizing, okay, I need to brominate something somewhere. I know it's not a radical, and I know I can attack bromine with nucleophiles, so that gives me a clue that I need some nucleophiles somewhere. But in this reaction, we changed the pH. We went from acidic, where we had this enol tautomerism type thing, to basic. And basic makes a big difference. When we get to the aldol, the base will make all the difference. So in this first step, the base will deprotonate at the alpha position. And somebody will ask me, why doesn't the hydroxide go for the carbonyl? And the answer is it does. Yes, the hydroxide will go for the carbonyl, very much like making a hydrate, but what's going to happen after that? It's going to go backwards. It's reversible. And we will find after the exam that there are many processes which are shuttling backwards and forwards, and eventually the system finds its way to, okay, I'm stable, I'm over here, I'm going over here. And all the rest of the molecules find their way over there. Even if you have 15 different pathways possible, you end up in the best place. That will get more interesting next week. So, yes, we can attack at the carbonyl because, of course, the OH is nucleophilic and the carbonyl is electrophilic, but that is a reversible system. And we're going to go somewhere that allows us to get rid of Br2. What was the problem with Br2? What do we like about Br2? What's the advantage of breaking that bond? What do you know about Br-Br bonds? They're weak. They're very weak, right? So the overall motivation here is to break that bromine-bromine bond and to get to somewhere more stable. So this CBr bond at the end will be more stable. So what we'll do here is argue that the proton at the alpha position is moderately acidic, about maybe 19 pKa on a ketone, and we'll be able to take it off and set up an equilibrium. And the whole point here, we've taken a base that allows the equilibrium to form. We get the enolate, which we can draw as two resonance structures, one in which has charge on carbon, the other of which has the charge on the oxygen. And then, I've said this several times, I'll say it again, all the chemistry that you will see from me this semester involves alpha carbon alkylation, or chemistry at the alpha carbon. We won't be putting anything on oxygen in this class. So we'll get some nucleophilic species going after Br2. And what does that remind you of? I mean, look at that system. Just give me a simple idea of what that mechanism reminds you of. Very basic fundamental mechanism that you've seen many, many times. SN2. It does look like an SN2, yeah? It's got the identical characteristics of an SN2. Bimolecular, nucleophile coming in, hitting the electrophile, kicking out a leaving group. That looks like an SN2. So that gives us the product. And that product is an alpha bromoketone. Yeah? All we did here was change the pH. If you understand a little bit about pH, you have a really good chance of doing these mechanisms, even if you haven't seen the mechanism before. If you don't understand pH, I might as well be writing in hieroglyphics. Okay? Understand pH and you can get a good start on this stuff. So we've changed from acid, where we did H plus and Br2, and now we've done the counterpart where we did the base with Br2. You get the same outcome, but again, negative species. Everything along the reaction profile is negative to make sense of that. So what we can do here is do this iteratively. We can replace all of the hydrogens one by one by one after the other, iteratively. And we're going to see now that this is a very useful colorimetric test for certain types of ketone. Before the invention of NMR spectrometers after World War II and the idea of infrared becoming everybody's favorite friend, where it's a very cheap instrument, it's very easy to use, people had to prove what they had made by chemical tests, by turning them into other things that then logically said, okay, if I've made this, I must have had this to start with. And so these types of chemical tests we don't do so much anymore because we have the fancy instruments. Science is much easier because of that. But if you were trying to prove to somebody that you'd made a methyl ketone, this was a way to do it. Now at the top, I have nothing more fancy than a second attempt, or let's say an iterative attempt at brominating. Maybe I have an excess of the bromine. I have more Br2 than I need for one step. So in this case, what we can do is alpha-alpha dibromination. We can take off protons one by one, brominate, and then take the other one off and brominate, and we get a dibromide. So what we're setting up here is this process. But this is nothing more complicated than just doing the same thing again and again and again. And if you see that, it's a fun reaction, and it's very useful if you don't have an NMR spectrometer in your basement. You can take sodium hydroxide, and you can take excess Br2, and you can turn a methyl ketone into a carboxylic acid. What? It's a wonderful reaction because it's one of the first examples that you will have seen of carbon behaving as a leaving group. At the end of this reaction, this carbon is gone. And to complete this, I'll put in the byproduct, CH-Br3. Okay? If you use iodine, you get a yellow precipitate. And that only happens if you have a methyl group next to the ketone. If you have a CH2 group, it doesn't work, you don't have enough protons. If you have a methyl group, you get CHI3. And this is called a haloform reaction. Okay, if you were to make that, that's chloroform, CHCl3. If you want to make the iodoform, it's CHI3. And they tend to be colorful compounds, which then indicate the fact that you had a methyl ketone to start with. Now, why do you need a methyl ketone? You need 3 hydrogens at the alpha position, at the same alpha position for this to work. That's going to end up with this thing breaking off. You're going to brominate, 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 leave. That's all there is to the haloform reaction. So the name is fairly obvious, the certain halide that you're using, and because this is chloroform, iodoform, that's where the name comes from. So to do this, we need base. And I quite often will write this with excess, just to make sure you recognize that this will happen again and again. At the end of this, we'll have to protonate something. You'll see why in a second. It's very similar to what we just did with the saponification reaction a while back. You'll end up with a carboxylate. You protonate it, you get your products. So the way this works is as follows. So this is complicated, but it isn't. I would hope that those of you who are getting into this and starting to recognize that there are repeats here, that things start to seem to add up, and we're not seeing any different intermediates, not seeing any wacky mechanisms that you haven't seen before, we can handle this. So the very simple requirement for this to work is a methyl group right here. You have to have 3 protons there, and they have to be next to the ketone. They have to be next to the ketone because that makes them acidic. And then we can take them off and we can replace them with halides. And we'll do that 3 times. And we'll end up with a CBr3 group at the alpha position. And that CBr3 group, or CI3 group, happens to be a decent leaving group. Methyl itself is a lousy leaving group. We've argued that many times. You bring in methyl minus like a Grignard, it's stuck and it's not coming back off. But you replace those hydrogens with I3 or Br3, all of a sudden this can take off. This can come back off. Only at high pH, but it can break back off. Now let's explain this. There is the sort of basic chemistry of the first step. You need a halogen. Typically, iodine is the most common one, or it gives you a nice bright yellow precipitate, so that's very useful because that's a dead indication of the fact that you have a methyl ketone to start with. So if this group over here is anything other than methyl, this won't work. Hydrogen, no. Benzene, no. It has to be CH3. And mixing the base and the halogen together, first of all, gives you the carboxylate salt. So all of a sudden we are swapping CH3 for O. Counterintuitive so far, but once I tell you that the leaving group's okay, it'll be all right. And this is the thing that is colorful. Often precipitates, there's your test. So how do we get there? That seems to be an awful lot of chemistry happening to be able to do so. But what I want to argue now is that it's the same thing that we just did, but we're going to do it 3 times. And then we're going to do a nucleophilic acyl substitution, and we're going to get a product. If you're memorizing these things, good luck to you. If you're starting to see things in a good sense, this is going to be straightforward. So here's my mechanism. We have a methyl ketone. The pKa of the protons on that methyl ketone are about 19. The pKa, the conjugate acid of hydroxide, is about 16. So I'm not too far away, right? 19 and 16. I can think about setting up an equilibrium here. So mechanistically, and I didn't put any arrows on here because I want to do it this way, I'm going to go after that proton. And I'm going to take that proton off. And I'm going to put some charge on the alpha carbon. That alpha carbon can stabilize itself because it's next to a ketone. I draw that second resonance structure to describe that overall charge. It is somewhere between the structure on the left and somewhere like the structure on the right. Which of those pictures do you think is more significant, left or right? The right, Grenza, because there's more charge on the oxygen. You want more charge on the oxygen. But if you were to draw a resonance hybrid, you'd probably draw dashed lines like we did last semester, and then put delta negative on O and delta negative on C. You have a nucleophile that is nucleophilic in 2 places. In my class, everything goes to the carbon because you get the carbonyl back. That's more stable. So to get from these pictures to the next molecule, I need to do an alpha halogenation. We'll go from here, and we'll jump over the box, and we'll go to there. And we'll do what looks nothing more fancy than an SN2 reaction to give an alpha halogenation. That's all it is. Deprotonate, brominate. So we got to the alpha bromo compound. If we just had the one equivalent of the bromine, we'd probably stop there. But we don't. We have an excess. We've dumped a lot of base in. We've dumped a lot of bromine in here. We can go again. So in the second step, the base comes in, goes after the proton, dumps the charge onto the carbon. Same as the first step, deprotonation, yes. Gives us an enolate, which is somewhere in between those 2 pictures. Same argument about the one on the right probably is more significant. It looks more like that, but certainly both of them are negative. So let's get down to this part. We now have a resonance stabilized anion. I would argue again that the conditions here are high pH, everything is basic, so everything along the reaction profile should be negative, and so far it is. Again, we have excess bromine. So we've made this species, and again, we have bromine available. Why would it want to do this? Because bromine-bromine bonds are weak. They always have been. It's always been good to break them. So let's do what looks like an SN2 reaction. Take a nucleophile, go after Br2, and break off Br-. That gives me an alpha-alpha dibromide. The alpha-alpha dibromide is, again, should be getting boring now because that's the same thing again. You have a base. You have a third proton. If you go after the proton with the base, you'll do an acid-base reaction. You'll take this thing off and you'll produce a negative charge on carbon, which is spread out as shown by that enolate structure right there. Same idea. All I've done is swap out bromines along that profile. Now, the last step to get to this guy is the same again. We have a nucleophile. I'll do this time just because I can. I'll go over the box. I'll do that. And I'll do that. SN2 reaction. And I'm left with the product of the iterative bromination, an alpha-alpha-alpha tribromide, alpha-alpha-alpha bromoketone. Now, there is something special about this system. That is a decent leaving group. It is not a great leaving group. Okay? It's not as good as Br-. It's not as good as H2O+, stuff like that. But it's good enough to break off at high pH, because we have already set this up so that unstable systems like hydroxide are there. They live in this system. So we can say that this now can be a decent leaving group. So to finish that off, we need to kick it out. And that's where the book has a slide. You do have this slide. If we have taken, and you can see why they chose this example, what would happen if you had more protons on this side of the molecule? You get more deprotonation and more bromination. It could get messy. But if you've set it up so that there isn't a proton here, and this will be important when we get to the aldol chemistry, being able to identify substrates that don't have protons there, we're stuck. We can't do any more acid-base chemistry. There aren't any protons to take off. So then the hydroxide switches roles. Where it was a base in the first few steps, it's now a nucleophile. And again, hydroxide is pretty unstable. It wants to react with something. So let's go after the carbon and do this type of addition. And this is where things can get quite complicated if you're not careful with the language. It's a ketone. Do ketones do addition or substitution? They do addition, except this one. You are going to now think about the possibility of CBr3- breaking off as a leaving group. So this is a rare example of a ketone doing acyl substitution. It can only happen under certain circumstances. These are those circumstances. So now we can see here, what would you call this species? That's a tetrahedral intermediate. And this is one very rare example where CBr3 or C- so far can break back off. And if we follow those arrows, we form a carbonyl right here, and the OH is right there. That's a carboxylic acid, and this guy. Now, why is it such a good leaving group? Well, you put the halogens on there. They're a little bit electronegative. They have orbitals that can be donated into, in terms of electron density being spread out a little bit better. They're not bad. They're not great, but they're not bad. So at the end of this, that's basic. It's only going to form at high pH. It's basic. It wants a proton. So in the last step of this process, you are going to take that as a base, take off that proton, because that's a pK of 5, and you get the carboxylate product, and you get the bromoform, which will be colorful. You'll be able to see it and say, hey, I had a methyl ketone. And then finally, what does H3O+ do? You have to neutralize this at the end. A carboxylate, and it gives you a carboxylic acid. So that acid at the end is just simply for that. If you look at that as a series of related reactions that you have seen already, it's just adding pieces together. It's molecular Lego. So there's your bromoform reaction, or haloform reaction in general. 3 alpha halogenations followed by an acyl substitution. So we'll move on. So far, everything has been about the alpha carbon. Everything has been about deprotonating next to the carbon. The alpha carbon is the key to the rest of the term, and it's a huge amount of biochemistry. So again, we need to be happy with the pH of the system. We need to be happy with the possibilities in terms of what can happen at that alpha carbon and where it can go next. We did spend on Friday quite a bit of time setting up the type of base to use. And we said that if you use a weaker base, you'll get an equilibrium. And if you use a stronger base, it won't be an equilibrium. It will go all the way to product. And then you can do something else with that product. Now, these aldol reactions, this is not a person's name. There was no Professor Aldol. Okay? It's the name of the product. The product is part aldehyde, part alcohol. Aldol. So it doesn't need to be capitalized. What's going to happen here is the first example of an intermolecular reaction in which the starter material serves as both components. It provides you with the nucleophile and the electrophile. And you get a system in which we have basically made the molecule twice as big. It's very powerful. We're going to say that the alpha protons here have to have a pK in the 19, 20, 21 region, 17 maybe for the aldehyde, so that this type of base is able to take it off. So we know that works. And what's going to happen, and I'll try and do this carefully, you're going to make that bond. Okay? You're going to make that bond. That is very powerful. You're going to make a bond between the alpha carbon of the one piece and the carbonyl carbon of the other piece. So the enolator is going to behave as a nucleophile, and the carbonyl is going to behave as the electrophile. And it's absolutely dependent upon this being set up. If you don't have an equilibrium, you can't do this. Does that make sense? If you set this up whereby every proton comes up, every molecule of that aldehyde all you have is enolate. You don't have any carbonyl left. There's no electrophile left. So you set it up with a base that allows for an equilibrium to set up, and away we go. It's a reaction in which alpha deprotonation is a key. You can do this in acid and base, and we can form an enolate. What's missing from this picture, which I'd like to see? A resonance structure showing where that charge can delocalize. Now, this is key. We have set it up so they have both in here. We haven't got just this. We've got some of this left because it's an equilibrium, going backwards and forwards. And we'll say now that this starter material that's left over can behave as the electrophile in this next step. And this nucleophilic addition, you go back and look at cyanide, you go back and look at Grignard's, negative carbon going after a carbonyl. That's nothing more fancy than that reaction. So this over here is an R group, if you like. But that R group has to be there as a carbonyl, or else the alpha protons aren't acidic enough. So we get a reaction in which nucleophilic attack happens from the alpha carbon to the carbonyl carbon of the conjugate acid. That gives you this, a new carbon-carbon bond forming reaction. Do this in the lab all the time. Biology is doing it all the time. It's incredibly useful. At the end of this, we have an alkoxide. The alkoxide needs to be quenched, but we've done this in a setup in which we have water in there. It's a high pH, so everything should be negative. I think that's okay. Everything along that reaction profile is negative. And then if we protonate with water, we end up with this, a beta-hydroxyaldehyde. The geography and the names of these things will be very simple if you understand that language, but it can be messy if you don't. At the alpha carbon here, nothing. At the beta carbon, hydroxy, beta-hydroxyaldehyde. Now, depending upon the conditions, that will stay or it will go someplace else. We're working up to that. So with that in mind, we can set these reactions up, and we can look at some of the problems of these reactions. We can look at an aldehyde versus a ketone. And at the top, we're saying that if you mix this aldehyde with base and water, setting up an equilibrium so that one goes after the other, and we get the nucleophile and the electrophile from the same material, we get a mixture that contains 75% of the aldol product, and 25% of the aldehyde is left. That's simply because it's going backwards and forwards. And when we see the mechanism here, we'll recognize that this is reversible. If I had a negative charge there, and I come back down and break this off, again, carbon's behaving as a leaving group. But in this case, it's breaking off because it can be delocalized. Yeah, the answer is you get mostly the aldol product. Because guess what? You're swapping a double bond here for a single bond here. And that usually is a good thing. Single bonds are stronger. But still you have some aldehyde left over. At the bottom, it's the opposite way around. If you mix a ketone, as exemplified by cyclohexanone, under those conditions, you get mostly the ketone left over and only a little bit of the product. And again, it's reversible. So this comes back down to very simply, what is more stable, an aldehyde or a ketone? And what happens when you have ketones that go to things like acetals or hydrates? We get problems in terms of steric environment. So at the top, the aldehyde is stabilized by this group, but not by this group. And you're swapping a double bond here, a pi bond, I should say, for a single bond. So this side is favored. There's nothing particularly helping the molecule on the left, and the molecule on the right is good because we have this new single bond. Down at the bottom, it's the opposite. Down at the bottom, we have two stabilizing groups. Two alkyl groups help stabilize that ketone. That helps the ketone be favored. But also on the right-hand side, I'd argue this is starting to happen over here, just like it did for hydrates. So that is destabilizing the outcome there. So on the bottom, the ketone is favored. On the top, the right-hand side is favored. But what we have to be aware of now is how do we make this thing go further? How do we make this thing go to something useful? Once you've got this aldehyde or aldol product formed, we still have an acidic proton. And that proton can come off using the base that's available. And this is a key step. Okay, that retroaldol, that's the reverse of what we just did. Instead of adding it, you're breaking it back off. So we're now saying that this carbon is capable of acting as a leaving group, and the only reason why is because it's resonance stabilized. So the aldol is reversible in every sense. You can go forward to make the addition products, you can come back by breaking the thing apart.